the polar bear reigns as the largest land predator today, reaching weights of up to 1,500 pounds. However, prehistoric Africa was home to an even more massive carnivore, Simbakubwa, an extinct giant that weighed as much as 2,200 pounds. Its story extends beyond sheer size. The extinction of Simbakubwa and other prehistoric giants has profoundly influenced modern African ecosystems, leaving an ecological legacy that scientists are still striving to fully understand. As we travel back 22 million years, we step into an Africa vastly different from the one we recognize today, a land where Simbakubwa, meaning big lion in Swahili, was the dominant predator. Yet, despite its name, Simbakubwa was not a lion at all. It belonged to an extinct lineage of carnivores known as Hyaenodonts. This diverse group thrived across Africa and Eurasia for over 40 million years before giving way to modern carnivores. Simbakubwa was uniquely adapted for its role as a top predator, showcasing remarkable features that made it an efficient hunter. One of the most distinctive aspects of this creature was its dentition. Unlike contemporary carnivores that possess a single pair of meat-slicing teeth, Simbakubwa had 3 pairs of specialized teeth. This unique dental arrangement, combined with a robust skull, enabled it to crush bones and take down sizable prey with ease. Its powerful bite force allowed it to tackle animals that would challenge even today's largest predators. Among its likely prey were early proboscideans, such as mastodons, which were ancestors of modern elephants. The presence of such an apex predator had significant effects on its ecosystem. Simbakubwa's reign would have influenced the behavior and evolution of other species in its environment. Prey animals had to adapt, developing new strategies to evade becoming meals for this giant hunter. This evolutionary pressure could have prompted changes in herd behavior, habitat preferences, and physical adaptations among herbivores. However, like all great predators, Simbakubwa's time eventually came to an end. The exact reasons behind its extinction remain a subject of scientific debate. Some theories suggest that ecological changes played a role, while others point to competition from newly evolving carnivores that were better suited to the changing environment. The disappearance of Simbakubwa created a significant ecological gap in ancient Africa. The extinction of such a dominant predator triggered ripple effects throughout the ecosystem. Prey species that had evolved under the constant threat of Simbakubwa found themselves in a transformed environment, leading to shifts in population dynamics among herbivores. These changes likely affected vegetation patterns across the landscape. The story of Simbakubwa serves as a powerful reminder of the intricate balance within ecosystems. The presence or absence of a single species, especially an apex predator, can have profound and lasting consequences. Even after its extinction, the evolutionary pressures exerted by Simbakubwa continued to influence the development of African wildlife for millions of years to come. The absence of Simbakubwa triggered an unexpected ecological transformation, leading to the rise of new dominant species. With the fall of this apex predator, a remarkable shift in the African landscape began, allowing the evolution and proliferation of megaherbivores, such as elephants, rhinoceroses, and giant giraffes. These colossal plant eaters became the powerful architects of their environment, drastically reshaping ecosystems with their feeding habits and immense physical presence. Megaherbivores, like elephants, had a profound impact on their surroundings. Their massive appetites enabled them to topple trees and clear vast swathes of vegetation, creating open spaces within previously dense forests. This alteration in habitat structure fundamentally changed the African landscape, paving the way for the iconic savannas we recognize today. By grazing and browsing, these giants prevented the overgrowth of certain plant species, helping to maintain a delicate ecological balance. As megaherbivores traversed their habitats, they created natural pathways through thick vegetation. These trails facilitated movement not only for themselves, but also for smaller animals, improving access to food and water resources. Consequently, the actions of these massive herbivores indirectly benefited a wide array of other species, enhancing biodiversity. One of the most significant contributions of megaherbivores to their ecosystems was the nutrient-rich dung they produced. The enormous quantities of plant matter consumed returned to the soil in the form of droppings, enriching the ground and supporting diverse plant life. These nutrient hotspots became essential for the growth of various plant species, further influencing the vegetation patterns across the landscape. The presence of megaherbivores created a mosaic of habitats that fostered a diverse range of animal species. Open grasslands emerged alongside scattered woodlands, providing distinct niches for various creatures. Species that thrived in open environments flourished in the clearings, while those preferring edge habitats found refuge in the transitional zones between cleared spaces and denser areas. This dynamic shift in ecosystem interactions, initiated by the rise of megaherbivores, significantly impacted African biodiversity. Their interactions with the environment spurred the evolution of new plant species that developed defenses against intense grazing pressure, such as thorns and chemical compounds. This evolutionary arms race prompted adaptations in the digestive systems of herbivores, driving the diversification of both flora and fauna. Beyond their immediate effects on vegetation and smaller animals, megaherbivores also influenced the hydrology of their habitats. By creating and maintaining waterholes through their wallowing behavior, elephants and rhinos provided vital water sources for a variety of species, especially during dry seasons. This further shaped wildlife distribution and survival patterns across the African landscape, demonstrating the far-reaching consequences of the megaherbivores' reign. As elephants and rhinos crafted oases across the African continent, a profound transformation was unfolding. Envision a world where the simple act of feeding could trigger significant evolutionary changes across countless species. The dining habits of these prehistoric giants played a pivotal role in nurturing one of Earth's most vibrant ecosystems. The savanna, with its rich mosaic of grasses, trees, and shrubs, created a variety of niches that various animals could exploit. From tiny insects to massive mammals, each species found its role in this intricate ecological tapestry. As the savanna evolved, it became a fertile ground for unique evolutionary adaptations. The challenges presented by this environment spurred the development of specialized traits in both flora and fauna. A remarkable example of the plant-animal interactions within the savanna is the relationship between acacia trees and ants. Certain species of acacia have evolved hollow thorns that serve as protective homes for aggressive ants. These ants fiercely guard their trees against herbivores, acting as a personal army. In exchange, the acacia provides shelter and food, such as nectar, showcasing the intricate connections that define the savanna ecosystem. Predators also adapted to the new landscape. The expansive open areas of the savanna offered minimal cover for stalking prey, leading to the evolution of innovative hunting strategies. Some predators developed remarkable speed and stamina, allowing them to chase down prey over long distances, while others became adept at camouflage, seamlessly blending into the golden grasses to ambush unsuspecting animals. Birds found abundant opportunities in the savanna mosaic. Many species adapted to life in grasslands, developing long legs for running through tall grasses, while others utilized scattered trees as vantage points or nesting sites. This variety of habitats fostered a remarkable range of avian life, from tiny seed eaters to large raptors. Most intriguingly, the savanna played a crucial role in the evolution of our early ancestors. Early hominids inhabited an environment that presented both challenges and opportunities. The open grasslands offered clear visibility for spotting predators and prey, while the scattered trees provided refuge and food sources. This unique combination is believed to have significantly influenced the development of bipedalism, tool use, and other traits that eventually led to the emergence of modern humans. The savanna ecosystem also became a battleground for an evolutionary arms race between plants and animals. A notable example is the relationship between mopane trees and elephants. To deter elephants, mopane trees evolved hardwood and bitter-tasting leaves. In response, elephants developed strategies to overcome these defenses, using their tusks to strip the bark and access the nutrient-rich cambium layer beneath. It's essential to understand that the savanna mosaic is not a static environment. It is a dynamic ecosystem continually shaped by the interactions between plants, animals, and environmental factors. These ongoing relationships contribute to the maintenance and evolution of the savanna's rich biodiversity, ensuring its resilience amid changing conditions. The balance of the savanna ecosystem is influenced not just by current living organisms, but also by the historical legacy of extinct species. Picture a world where the shadows of ancient predators linger, subtly guiding the behavior of their modern prey. This is not mere imagination. It reflects the reality of Africa's ecological landscape, where the effects of ancient carnivores continue to shape animal behavior millions of years after their extinction. Despite the disappearance of formidable predators like Simbakubwa, their evolutionary impact persists in unexpected ways. Modern prey species, which never encountered these prehistoric giants, exhibit behaviors that evolved as adaptations to their former presence. This phenomenon illustrates how deeply evolutionary pressures can imprint on ecosystems over time. For instance, many herbivores in Africa tend to prefer open grasslands over denser vegetation, even in the absence of large predators. This behavioral trait likely stems from adaptations developed to evade ambush tactics employed by ancient carnivores, influencing the patterns of vegetation throughout the savanna. The concept of the landscape of fear serves as a useful lens for understanding the enduring influence of predator behavior beyond direct predation. In African ecosystems, this is evident through specific behaviors exhibited by herbivores. Some species actively avoid areas with few escape routes or prefer to graze on elevated terrains, strategies that would have once minimized their vulnerability to ground-dwelling predators. These inherited responses create intricate patterns of herbivore distribution and activity. Consequently, certain regions may experience increased grazing pressure, while others remain relatively untouched, all dictated by perceived risks that no longer align with actual threats. This uneven impact leads to varied vegetation densities, ultimately affecting plant diversity and distribution. The legacy of extinct predators also manifests in modern species behaviors. For example, some herbivores exhibit heightened vigilance during nighttime, a trait essential for survival when nocturnal predators like Simbakubwa roamed the savanna. This continued caution influences their feeding patterns and energy use, which can indirectly affect population dynamics. Conservation strategies in African ecosystems must take this historical context into account. Habitat restoration and species reintroduction projects should consider these ingrained behaviors. Creating structures that mimic elevated safe zones may encourage herbivores to more effectively utilize restored areas. The persistence of these adaptations raises intriguing questions about evolutionary plasticity. How quickly can species adjust when ancient threats vanish or new ones emerge? Understanding these enduring behavioral adaptations offers valuable insights into the hunting strategies and ecological roles of long-extinct predators, allowing researchers to bridge millions of years of evolutionary history. The influence of prehistoric predators extends far beyond observable behaviors, reshaping entire ecosystems, including the very nutrients within the soil. The absence of ancient carnivores like Simbakubwa has initiated profound transformations in modern plant and animal life, revealing complex interactions that scientists are only beginning to uncover. The extinction of mega-carnivores has notably affected soil chemistry and patterns of plant growth across African landscapes, leading to significant ecological repercussions. One of the major impacts has been a decrease in nitrogen and phosphorus concentrations in certain areas, altering the pH balance of the soil. This shift has favored specific plant species while disadvantaging others. A compelling example of this ecological transformation is seen in the distribution of acacia trees. These trees depend on high nitrogen levels in the soil and have become less prevalent in regions that were once active hunting grounds for large carnivores. Conversely, grasses that thrive in nutrient-poor conditions have expanded their territories, dramatically altering the vegetation landscape. The changes in soil composition have also had unforeseen effects on smaller animal species. For instance, dung beetles, vital for nutrient cycling, have seen population fluctuations due to shifts in dung sources from predators to herbivores. This alteration affects soil aeration and nutrient distribution on a microscale, further influencing plant growth patterns across the savanna. The legacy of extinct mega-carnivores continues to shape modern African ecosystems through the intricate relationships between soil, plants, and animals. For example, the uneven distribution of calcium and phosphorus, remnants of ancient predator activities, still affects the mineral content of plants, which in turn influences the health of herbivores that depend on them for sustenance. Incorporating historical soil composition changes into modern conservation efforts is crucial. As we strive to protect and restore African ecosystems, it's essential to consider not only existing ecological relationships, but also the long-term effects of past extinctions. This historical context can guide strategies to maintain soil health, manage vegetation, and support diverse animal communities amidst ongoing environmental challenges. Recent studies have shown that regions with a history of high predator activity often feature unique soil microbiome compositions. These microbial communities are essential for nutrient cycling and plant vitality, affecting everything from disease resistance to drought tolerance in local flora. Increasingly, conservation efforts emphasize the preservation of these microbial legacies as part of a comprehensive approach to ecosystem management. The story of soil composition in African ecosystems underscores the interconnectedness of all living things. It illustrates how the extinction of a single group of animals can trigger a chain reaction that reverberates throughout an ecosystem for millions of years, influencing even the most minute soil particles. Continued research into these complex relationships fosters a deeper understanding of the delicate balance of nature and the enduring impact of ecological changes. As we delve into ecological history, a fascinating aspect of plant evolution comes to light. Rather than being mere bystanders to animal extinctions, the grasses of Africa may have been active participants in an ongoing evolutionary struggle. The emergence of mega-herbivores in Africa catalyzed an extraordinary evolutionary arms race between plants and their consumers. This intense pressure prompted the evolution of grazing-resistant plants, especially grasses, which developed innovative defenses beyond physical barriers. One remarkable adaptation found in some African grasses is the presence of endophytic fungi. These microscopic organisms reside within the plant tissues, producing alkaloids that deter herbivores by rendering the grass toxic or unpalatable. This symbiotic relationship offers a chemical defense mechanism distinct from physical deterrence, showcasing the complexity of plant adaptations. As grasses evolved new defenses, herbivores also adapted in response. For instance, certain African antelopes, like the gerenuk, developed elongated necks and the ability to stand on their hind legs, enabling them to reach leaves and fruits beyond the grasp of other grazers. This adaptation allowed them to sidestep competition for ground-level vegetation, illustrating the ongoing coevolution of plants and herbivores. The dynamic interplay between grazing pressure and plant defenses has significantly shaped the composition of African grasslands. Diverse plant communities emerged, each exhibiting unique adaptations. The whistling thorn acacia, for example, formed a mutualistic relationship with ants, providing them shelter in exchange for protection against browsing animals. Such adaptations have also influenced the dietary habits and behaviors of herbivores across the continent. The aardvark exemplifies this shift, evolving to feed on ants and termites, thus indirectly benefiting from the increased insect populations supported by varied plant communities. This dietary change highlights a unique evolutionary response to the evolving dynamics between plants and herbivores. The legacy of these evolutionary processes is evident in today's African flora and fauna. Modern savanna ecosystems display a complex web of interactions, from the communal grazing patterns of wildebeest to the specialized feeding habits of giraffes, all shaped by millennia of coevolution with resilient plant life. Understanding these intricate adaptations is vital for effective ecosystem management. As we confront challenges like climate change and habitat loss, insights into plant-animal coevolution can inform conservation strategies, emphasizing the need to maintain diverse plant communities to preserve the delicate balance of savanna ecosystems and support the survival of both grazers and the grazed. Conservation efforts often emphasize the visible aspects of ecosystems, but beneath the surface lies a significant legacy shaped by prehistoric giants. How did these ancient titans influence the very water sources that dictate wildlife patterns across Africa? The answer reveals the profound effects of ancient megafauna on the continent's hydrological landscape. Millions of years ago, enormous herbivores, including early elephants and rhinos, roamed the African plains, their immense bodies and behaviors reshaping water resources in remarkable ways. As these colossal creatures traversed the landscape, they created and maintained vital water holes that became crucial for countless species. For instance, an elephant, weighing several tons, would dig into dry riverbeds or depressions using its tusks and feet. Over time, this behavior formed substantial depressions that could collect and retain water during rainy seasons. Even after the rains ceased, many of these water holes continued to exist, sustained by underground aquifers. This natural process, repeated over millennia, resulted in a network of life-giving oases. These water sources, shaped by megafauna, became focal points for entire ecosystems. A diverse array of animals relied on these crucial water holes, significantly influencing migration patterns and species distributions. Herbivores planned their movements around these reliable water sources, and predators, in turn, followed their prey. Additionally, the influence of extinct megaherbivores extended beyond the mere creation of water holes. These massive animals played a key role in maintaining open channels within river systems, preventing the overgrowth of vegetation that could otherwise choke off vital waterways. In wetlands, their heavy footfalls and feeding behaviors fostered a mosaic of microhabitats, each supporting unique communities of plants and animals. However, the extinction of many megafauna species led to significant changes in the hydrological landscape. Some water holes filled with sediment or became overgrown, while river channels once kept open by these massive creatures started to narrow and change course. Despite these alterations, many ancient water sources have persisted, continuing to support biodiversity and influence animal behavior patterns. Recognizing the long-term impact of these ancient giants is essential for modern conservation efforts. In South Africa's Kruger National Park, researchers have identified ancient water holes created by extinct megafauna. Conservation managers now prioritize the maintenance of these historically significant water sources, employing strategies such as controlled burning and selective vegetation removal to mimic the ecological effects of ancient herbivores. Similarly, in Hwange National Park, Zimbabwe, conservationists have implemented a water management plan inspired by the historical role of megafauna. They maintain a network of artificial water holes, strategically positioned to replicate the distribution patterns established by ancient herbivores. This approach has proven effective in sustaining wildlife populations during dry seasons and influencing animal movement across the landscape. Modern elephants and other large herbivores continue to fulfill a similar role in maintaining water sources, albeit on a smaller scale than their prehistoric counterparts. In Botswana's Okavango Delta, for example, researchers have observed how elephant activities help sustain channels and lagoons, benefiting a wide range of species. Protecting these contemporary ecosystem engineers and the habitats they influence is crucial, especially in light of their role in perpetuating the ancient hydrological patterns that shaped the African landscape. In our efforts to protect today's ecosystem engineers, it's crucial to explore the significant ripple effects caused by the extinction of their massive ancestors. The disappearance of megafauna fundamentally reshaped entire ecosystems, creating unexpected opportunities for the surviving creatures. This extinction event initiated a seismic shift in African ecosystems, leading to a surprising surge in biodiversity among smaller to medium-sized animals. One notable example of this diversification is the African elephant shrew, which proliferated into several distinct species following the extinction of larger herbivores. Despite their name, these small mammals are not closely related to elephants. Instead, they occupy ecological niches previously filled by their larger counterparts. The changed ecosystem created new evolutionary pressures and opportunities for these smaller creatures. For instance, the African crested rat evolved a unique ability to utilize toxins from certain plants, possibly as a defense mechanism in the absence of larger predators that once regulated their populations. This adaptation enabled them to thrive in environments where other small mammals might struggle. Bird populations also experienced significant changes due to shifts in their habitats and food availability. The loss of large herbivores altered seed and fruit distributions, impacting the diets of various avian species. The African green broadbill, for example, developed specialized beak structures to access food sources that became more abundant in the post-megafauna environment. However, not all species thrived in the wake of megafaunal extinction. Some animals that had co-evolved with these giants found themselves ill-equipped for the new ecological landscape. While the African aardvark did not face extinction, it had to adapt its diet and behavior significantly to cope with changing ecosystem dynamics. The intricate interactions between large and small species continue to shape biodiversity in African ecosystems today. The legacy of extinct megafauna is evident in the adaptations of contemporary species, many of which retain traits that evolved in response to these vanished giants. Understanding these historical relationships is essential for predicting how ecosystems might react to future changes, such as those driven by climate change or human activity. A fascinating example of ongoing influence is seen in the relationship between dung beetles and large herbivores. Following the extinction of many large animals, dung beetle populations faced significant challenges. Over time, however, they adapted, leading to a diversification of species. The Scarabaeus zambesianus, for instance, evolved to specialize in quickly burying elephant dung, a skill that became vital in the new landscape. Moreover, the extinction of megafauna had surprising repercussions for seed dispersal patterns. With the loss of these animals, certain plant species encountered difficulties in seed distribution. The African calabash tree, with its large gourd-like fruits, likely relied on megaherbivores for seed dispersal. Today, smaller animals such as baboons and elephants play a role in this process, but the tree's distribution has been significantly affected. By examining the cascading effects of megafauna extinction on smaller species, we gain valuable insights for modern conservation efforts. This highlights the interconnectedness of ecosystems and the far-reaching consequences of losing key species. In light of current biodiversity crises, understanding this historical context can inform strategies aimed at protecting not just individual species but entire ecological networks. Although climate change is often viewed as a contemporary issue, its origins can be traced back millions of years. The extinction of megafauna has left an enduring mark on Africa's ecosystems, influencing how they respond to global climate shifts in unexpected ways. The disappearance of large herbivores, such as early elephants and rhinos, initiated a series of ecological changes that continue to shape African landscapes today. These ancient giants played a vital role in maintaining the ecological balance, helping to shape habitats and vegetation patterns. Their extinction caused significant shifts in plant life and soil composition, which in turn altered the carbon storage dynamics of various environments across the continent. Regions that once thrived as open grasslands due to the grazing of megaherbivores have gradually transformed into more densely wooded areas, fundamentally changing their interactions with the global carbon cycle. Furthermore, the absence of these large animals has impacted local climate patterns. By creating a mosaic of open and closed habitats, they regulated temperatures, rainfall distribution, and fire frequencies. The resulting changes in vegetation structure continue to influence how African ecosystems respond to and mitigate climate change today. The legacy of extinct megafauna offers crucial insights into ecosystem resilience. Paleontological research has shown that regions once inhabited by diverse megaherbivores displayed greater resistance to climate-induced shifts in vegetation. This understanding is now guiding the formulation of climate-resilient conservation strategies across modern African landscapes. Some innovative conservation projects are actively drawing from historical precedents. In Namibia, for instance, initiatives to reintroduce large herbivores to arid regions aim not only to enhance biodiversity, but also to restore ancient grazing patterns that foster drought-resistant vegetation. Similarly, in South Africa, conservationists are working to maintain mixed-feeding herbivore guilds, seeking to replicate the varied impacts of extinct megafauna on plant life. This approach may bolster the ecosystem's ability to adapt to changing climate conditions. The influence of extinct megafauna extends into evolutionary adaptations among plants. Many species that co-evolved with these large browsers developed traits that now affect their resilience to climate changes. For example, certain African acacia species have retained thorns and chemical defenses against large herbivores, influencing their survival under current climate stresses. As we navigate the complexities of climate change, the lessons learned from the extinction of megafauna offer both warnings and potential solutions. Their cascading effects underscore the intricate relationships between species and their environments, highlighting the far-reaching consequences of biodiversity loss. Insights from these ancient ecosystems can inspire innovative management strategies and climate mitigation approaches, demonstrating how the past can inform our responses to future challenges. The remnants of extinct megafauna continue to exert influence on our planet in ways that often go unnoticed. Imagine the potential of harnessing this ancient impact to address today's environmental challenges. A groundbreaking approach to conservation is taking shape, one that draws inspiration from the past to secure a more sustainable future. This innovative strategy, rooted in the study of prehistoric ecosystems, is offering profound insights for contemporary conservation efforts and reshaping our understanding of ecological management. The legacy of extinct megafauna presents a unique perspective from which we can assess and anticipate how ecosystems respond to modern changes. By examining the ecological roles these ancient giants once held, scientists are uncovering the intricate interactions that define our natural world. This deepened understanding is proving invaluable in crafting more effective conservation strategies that account for entire ecological processes rather than focusing on isolated species. Rewilding projects inspired by prehistoric ecosystems are already yielding remarkable results. For instance, in the Netherlands, the Oostvaardersplassen Nature Reserve introduced Hek cattle and Konik horses as modern analogs for the extinct aurochs and tarpons. This initiative has fostered a dynamic, self-regulating ecosystem that closely mirrors the grasslands of the prehistoric era. Similarly, in Siberia, the Pleistocene Park project aims to reintroduce large herbivores like bison and musk oxen to restore the mammoth steppe ecosystem. This reintroduction could potentially slow the thawing of permafrost and mitigate climate change. Research into extinct megafauna is also unveiling unexpected insights about present-day large mammals. Studies of fossil remains from giant wombat-like marsupials in Australia reveal that these creatures acted as ecosystem engineers, creating intricate burrow systems that provided habitats for numerous other species. This revelation is prompting conservationists to reconsider the role of modern wombats in fostering biodiversity and enhancing soil health, leading to new protective measures for these often overlooked animals. The examination of ancient megafauna is also illuminating previously unknown ecosystem processes. For example, research on extinct giant tortoises in the Mascarene Islands has highlighted their vital role in seed dispersal and the maintenance of plant diversity. This knowledge is now shaping conservation initiatives aimed at reintroducing the Aldabra giant tortoise to islands where they were once extinct, striving to restore lost ecological functions. The long-term consequences of past extinctions serve as a powerful reminder of the necessity of safeguarding current species. The disappearance of megafauna millions of years ago triggered a cascade of ecological changes that still reverberate today. This historical perspective emphasizes the potentially far-reaching consequences of modern extinctions, driving the urgency for more comprehensive conservation strategies. It's essential to recognize that contemporary African ecosystems are products of both historical and present influences. The landscapes we observe today have been shaped not just by current environmental factors and human activities, but also by the remnants of extinct species that once inhabited these areas. Understanding this dual influence is crucial for developing effective conservation strategies that honor both the historical context and the current realities of these ecosystems. Insights gleaned from the study of extinct megafauna are informing efforts to adapt to and mitigate climate change. By analyzing fossil pollen and plant remains associated with megafauna habitats, researchers are reconstructing past climate conditions and ecosystem responses. This data aids in refining climate models and predicting future ecological shifts, enabling conservationists to devise targeted strategies for preserving biodiversity amid rapid environmental change. The legacy of extinct giants continues to influence Africa's ecosystems in ways we are just beginning to comprehend. Their impact shapes modern species behaviors and the land's composition, highlighting the vital connection between past and present for effective conservation. As we confront significant environmental challenges, insights from ancient megafauna become crucial for developing comprehensive strategies. By embracing this long-term perspective, we can protect not only individual species, but also the intricate relationships that sustain life on Earth.